What if Earth isn't the ultimate home for life? What if, somewhere out there in the vastness of space, there exists a planet that could be even more suitable for life than our own? It sounds like science fiction, but scientists are now seriously exploring this possibility. Headlines are popping up everywhere. Scientists discover planets more habitable than Earth. They're calling it the biggest hint of alien life ever found. A planet 120 light-years away, and a 99.7% confidence signal that something unusual is happening in its atmosphere. The James Webb Space Telescope has just picked up molecules we've never seen on any other world. Molecules that, on Earth, are produced almost entirely by life. Not machinery, not volcanoes, not storms, life. In the last few days, the scientific world has gone from cautious curiosity to stunned disbelief. Is this the moment we've been waiting for? Did JWST just stumble upon the first real evidence that we are not alone? Or is the universe playing its most fascinating trick yet? Because hidden in the light of a distant red dwarf star, wrapped in the thick atmosphere of a strange Hycean world, lies a signal so perplexing, even the experts can't decide if it's biological or something we've never imagined. Stay with me, because in the next few minutes, we're diving into the discovery that could change everything we know about life in the universe, or expose one of the greatest scientific false alarms ever recorded. Welcome back to the channel where we explore the mysteries of our universe, one mind-bending discovery at a time. And today, we're diving into one of the biggest scientific shocks of the decade. A distant planet, a strange chemical fingerprint, and a telescope powerful enough to challenge everything we thought we knew about life beyond Earth. If stories about alien worlds, deep space secrets, and cosmic breakthroughs fascinate you as much as they fascinate me, you're in the right place. Drop your thoughts in the comments as we go. I love reading your theories, and feel free to share this video with someone who enjoys having their mind blown. Alright, let's get into it. Why this discovery matters. For decades, humanity has searched the skies with one question in mind. Are we alone? We've scanned radio signals, mapped thousands of exoplanets, and studied atmospheres light years away, yet every time we got close to an answer, the universe stayed silent. That's because detecting life is incredibly hard. We can't fly to distant planets. We can't scoop their oceans or sample their soil. Instead, scientists look for biosignatures, chemicals that, on Earth, are linked to living organisms. But even then, the signals are usually faint, uncertain, or explained by natural processes that have nothing to do with biology. That's why true biosignature detections are rare, and why this new observation has sent shockwaves through the scientific community. K2-18b, a planet discovered back in 2015, has always been interesting. It's a sub-Neptune, larger than Earth, possibly covered in a global ocean beneath a hydrogen-rich atmosphere. But for years, it was just one world among thousands. Then JWST took a closer look, and suddenly K2-18b was everywhere. Headlines, newsrooms, research discussions, scientific panels. Because JWST didn't just detect the usual atmospheric gases, it picked up hints of molecules that, on Earth, come almost exclusively from biological activity. And that's when everything changed. This isn't just another exoplanet. This isn't another maybe or possibly. This is the closest humanity has ever come to detecting a chemical fingerprint that could be linked to life beyond Earth. And the closer we look, the stranger it gets. Meet K2-18b. K2-18b lives about 124 light-years away, orbiting a dim red dwarf star. It completes one full orbit every 33 days, a tight, fast path compared to Earth's 365-day journey, yet thanks to the low luminosity of its host star, the amount of stellar energy it receives is roughly comparable to what Earth gets from the Sun. In terms of size and mass, K2-18b is dramatically different from Earth. More surface area also means more room for diverse habitats, especially if that surface includes a variety of shallow seas, lakes, or continents, rather than one deep ocean. Second, scientists pay close attention to the type and stability of the host star. Stars, smaller, cooler, and longer-lived than our Sun, often so-called K-dwarf or orange dwarf stars, may offer ideal conditions. Because they burn their fuel slowly, these stars provide a long, stable window, tens of billions of years, potentially for life to emerge and evolve. Planets orbiting such stars are less likely to experience catastrophic stellar flares compared with some smaller, volatile star types, offering more benign radiative and environmental conditions. Third, potential presence of water, ideally liquid water on the surface, remains central. Without water, life as we understand it likely cannot emerge. Thus, candidate planets are sought that not only lie in the so-called habitable zone, where surface temperatures allow water to stay liquid, but also have geophysical and atmospheric conditions that favor stable water retention across eons. Fourth, scientists consider climate stability, geological activity, and long-term habitability factors. A superhabitable planet ideally maintains stable conditions over billions of years, enough time for life to arise, evolve, diversify. That depends on things like a stable orbit, maintenance of atmosphere and magnetic field, tectonic recycling to support climate regulation, perhaps moderate but not extreme temperatures and weather cycles. But here's the catch: we don't yet directly see many of these features. Telescopes and detection methods give us approximate planet mass or radius, orbital distance, and star type, but not always atmosphere composition, surface water, magnetic field, or detailed climate history. Because of that, scientists must make predictions and models, using theoretical frameworks to estimate habitability potential, not certainties. In effect, every candidate is evaluated against a checklist of superhabitability traits: size, mass, star type, orbital zone, potential for water, internal and atmospheric stability, and ranked by how many criteria it meets. Planets that check many boxes become priority targets for future observations. This methodology doesn't guarantee life, but it helps narrow the endless cosmic field to a manageable shortlist of worlds that are the best bets for habitability beyond Earth. Promising candidate planets. Let's start with one of the most exciting discoveries of 2025, GJ251c. Imagine a planet that's just 18 light-years away from Earth, orbiting a star not too different from many in our galaxy, and yet potentially offering conditions that could rival or even surpass those on our home planet. GJ251c was unveiled in a study published in 2025. It's classified as a super-Earth, with a mass roughly 3.9 to 4 times that of Earth. What makes this particularly striking is that GJ251c appears likely to be rocky, not a gas giant, meaning its surface could, in principle, support solid ground. The planet orbits its host star in about 54 days, at a distance of roughly 0.196 astronomical units AU, much closer than Earth is to the Sun. But here's the key: its star is an M-dwarf, a red dwarf much cooler and dimmer than our Sun. Because of that, the habitable zone, the region where temperatures allow for liquid water, sits much closer in. GJ251c lands almost dead center in that sweet spot. That means, if GJ251c has the right kind of atmosphere thick enough to hold heat and water, it might sustain liquid water on its surface. Liquid water is widely considered essential for life as we know it. Let's compare with Earth for a moment. Earth has 1 Earth mass, orbits the Sun every 365 days at 1 AU, and benefits from a stable star whose output supports long-term climate and a protective atmosphere. GJ251c, on the other hand, is heavier, about 4 Earth masses, which could provide a stronger gravitational grip, helping the planet retain a dense atmosphere over long timescales. Its host star is dimmer and cooler, but its habitable zone is more compact, meaning GJ251c receives just the right amount of radiation to potentially maintain temperate conditions, assuming favorable atmospheric conditions. Because GJ251c is also relatively near, just about 18.2 light-years away, it becomes an ideal target for future observations. In fact, researchers say it's among the best candidates in the northern sky for direct imaging, with next-generation, extremely large telescopes currently in development. If astronomers can directly image GJ251c and detect clues of an atmosphere or water, that would be a game changer. But here's the dramatic thought. Imagine standing on the surface of GJ251c with a suitably Earth-like atmosphere. The planet is nearly 4 times heavier than Earth, so gravity would be stronger. The sky might look a bit different. The day-night cycle due to its orbit could feel alien, yet from its surface you might see a sunset across oceans or continents. A world that's heavier, different, yet hospitable, a cosmic what-if come true. And this is just the beginning. GJ251c raises hope that in our galactic neighborhood there may be other, perhaps even more favorable worlds waiting to be found. In the next sections, we'll meet some of those, but for now, GJ251c stands out as a shining example of what might await us beyond Earth. Other promising candidate planets. Next up, more of the universe's most intriguing candidates. Some of these are still maybes, but that very uncertainty makes them doubly fascinating. One such world is KOI 5755.01. This object remains a candidate not yet fully confirmed, but it checks many boxes that make scientists sit up and take notice. Its host star is a K-type slightly cooler than the Sun, a type that some researchers consider especially favorable for long-term habitability. KOI 5715.01 is thought to orbit at a distance and under conditions where its surface temperature could be around 11 degrees Celsius, assuming a decent atmosphere comfortably temperate by Earth standards. Its estimated age, star type, and theoretical equilibrium temperature earned it a place in a recent list of top superhabitable contenders. But because the planet is still a candidate, not all observational details can be trusted yet. That uncertainty is exactly what makes it thrilling. KOI 5715.01 could turn out to be a hidden gem or a false alarm. Only further observations will tell. It's a mystery wrapped in starlight. Then there's LHS 1140b, one of the most promising and seriously studied exoplanets to date. Orbiting a quiet red dwarf star, LHS 1140b seems to avoid the violent stellar tantrums that doom many red dwarf systems, making it a relatively calm neighborhood. Recent observations with advanced telescopes suggest that its density is lower than a typical rock-only world. That implies that a significant fraction, perhaps 10–20% of LHS 1140b's mass, could be water. In other words, this could be a water world, maybe even an ocean planet. Spectroscopic analysis hints at a possible nitrogen-dominated atmosphere similar in overall composition to Earth's, and the presence of a stable, temperate zone where liquid water could exist. If confirmed, LHS 1140b might be the best candidate yet for a habitable or even life-supporting world beyond our solar system. But there are caveats. The exact composition of its atmosphere is not yet confirmed. It could still be a mini Neptune with a thick hydrogen envelope, or a frozen snowball world, or something entirely unexpected. Until more observations come in, LHS 1140b remains promising and tantalizingly uncertain. Finally, there's Kepler 438b. When first discovered, many celebrated it as perhaps the most Earth-like planet yet found. Similar size to Earth, with a temperature allowing for liquid water, orbiting in its star's habitable zone. But further studies revealed a major problem. Its host star is very active, producing frequent superflares. These powerful bursts, potentially accompanied by coronal mass ejections, could strip away any atmosphere the planet had. Without an atmosphere, liquid water would evaporate or be destroyed, radiation would ravage the surface, and habitability would collapse. As a result, many researchers now believe that Kepler 438b, despite its initial promise, is unlikely to host life as we know it. What all these cases show is how delicate and uncertain the search for habitable worlds really is. Even planets that look ideal from a distance can turn out to be hostile once you dig deeper. Atmosphere, water, star behavior, magnetic fields, climate stability, all those factors matter, and often we simply don't have enough data. That's why astronomers present such candidate planets with caution. But that caution doesn't dampen wonder. If anything, it deepens it, because every one of these worlds, whether confirmed or candidate, represents a doorway to a cosmic what if. What if, somewhere out there, life has found a better home than Earth? What if habitable or even inhabited worlds are more common than we dared imagine? What we know versus what we don't. So far, astronomers have learned a surprising amount about distant exoplanets, but there is still far more that remains unknown. It helps to think of it as a cosmic ledger, columns for what we can say and what we can't yet say. What we know? For many of the candidate planets, we have reliable estimates of their size or mass. their orbit, how far they are from their star, the type of star they orbit, and their distance from us. These data come from methods like transit observations and radial velocity measurements. For example, we know whether a planet lies in the so-called habitable zone, the orbital region around a star, where, in principle, temperatures could allow liquid water on the surface. That gives us a first pass at which planets might be interesting. What we do not know, at least not yet, is often far more crucial. We rarely have direct measurements of a planet's atmosphere composition. We don't know whether there is water on the surface, oceans, lakes, seas, or only water vapor, or none at all. We cannot yet confirm whether the planet maintains a stable climate over geological durations, or whether it has a magnetic field to protect it from stellar radiation. We don't know if its surface is rocky, or covered with deep oceans or thick ice, or whether it has tectonic activity, all factors that affect long-term habitability. As a result, the idea of a superhabitable planet must remain theoretical. Even if a planet checks many boxes, right mass range, right orbit, right type of star, that does not guarantee it can support life. Such claims depend on many assumptions and models. That's why scientists say these worlds are candidates for habitability, not Earth twins or guaranteed life hosts. This gap between what we know and what we don't is not failure, it's opportunity. It invites us to ask bold questions. Could life exist under conditions very different from Earth's? Could there be life forms that thrive in climates or atmospheres we haven't even imagined? The unknowns challenge our Earth-centric assumptions and widen our view of what's possible. So when you see headlines about habitable planets, remember what lies behind them: a mix of solid data, careful inference, and hopeful imagination. The universe may hold more surprises than we can presently confirm, and that is what makes the search so thrilling. Implications of superhabitable worlds. What if our home planet, Earth, isn't the pinnacle of habitability, but just one among many possible good homes in the universe? The idea of superhabitable worlds forces us to confront that possibility. It suggests Earth may not be unique or supreme in supporting life. Instead, it might be average, or even suboptimal by cosmic standards. If superhabitable worlds truly exist, planets slightly larger or more massive than Earth, orbiting long-lived stable stars with temperate climates, shallow seas, or archipelago-style geographies, then life elsewhere could take root more easily and potentially flourish in greater abundance than on Earth. This challenges our Earth-centered assumptions. Maybe life doesn't need Earth's exact conditions. Maybe alien life, microbial, ocean-dwelling, forest-like, or even complex and intelligent, could evolve under conditions we consider alternative. Imagine a world with more gentle climates, milder seasons, extensive shallow seas and islands, a planet where tropical-like biodiversity is the norm across the entire surface. Such a luxury penthouse of habitability could allow ecosystems to thrive, diversify, and perhaps evolve complex life, maybe even intelligence. That expands our vision of life beyond the narrow Earth analog paradigm. What's more, the hunt for life and planets that host it is not just science fiction anymore. With the advent of powerful new tools like James Webb Space Telescope, JWST, and in future ground-based giants such as extremely large telescopes, ELTs, we now have the capacity to probe exoplanet atmospheres, search for water vapor, trace greenhouse gases, and even hunt for biosignatures, chemical fingerprints that might hint at life. One day, with enough observations, we might look up at the night sky and realize Earth isn't alone in offering the perfect home for life. We could discover planets where life isn't just surviving, it's thriving, evolving differently, perhaps flourishing in forms we haven't even imagined. That possibility redefines our place in the cosmos, not as solitary custodians of life, but as one among many life-bearing worlds. And it means the universe might be far richer, far more alive than we ever dared hope. Upcoming missions and observations. Since the success of James Webb Space Telescope, JWST, astronomers have entered a new era, one where examining exoplanet atmospheres, searching for water, and even hunting for signs of life, biosignatures, is becoming real. JWST's infrared instruments can analyze light that filters through a planet's atmosphere. As it transits, its star-letting scientists detect molecules like water vapor, methane, and carbon dioxide. These chemical fingerprints give clues about whether a planet might have the ingredients needed for life. But JWST is just the beginning. On the horizon are several powerful new observatories that promise to deepen and perhaps accelerate the search. The Nancy Grace Roman Space Telescope, Roman, planned for launch in the mid-2020s, will scan large portions of the sky in infrared, discovering many more exoplanets using techniques like microlensing and direct imaging. Roman's wide field of view makes it ideal for finding worlds that earlier missions might have missed. Then there are missions like Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, slated for launch in the late 2020s. Ariel's goal is to study the atmospheres of hundreds or even thousands of known exoplanets, mapping their chemical composition and thermal structure. That will help scientists understand which types of planets tend to have stable atmospheres, water, or other life-friendly features. Looking further ahead, future flagship missions like Habitable Worlds Observatory, HWO, planned for perhaps the 2040s, aim to push the envelope even more. With advanced coronagraphs or external starshade technology, HWO would directly image Earth-sized exoplanets in habitable zones around nearby stars. It might even detect faint reflected light from oceans or continents and search for gases like oxygen or methane that could indicate biological activity. What might these telescopes find? With high contrast imaging and spectroscopy, they could reveal atmospheric compositions, trace water vapor or clouds, detect greenhouse gases, and perhaps even uncover biosignatures. Over time, as more exoplanets are discovered and characterized, astronomers will build a richer catalogue of promising worlds, which might include superhabitable candidates.